So this video project of Jess Chen, Corinne Mayer, and Brianna Bristol. We are here to talk to you about vibrations, waves, and sounds. What you see right here is a pendulum, which is a weighted object suspended from a fixed point. Pendulums are able to maintain consistent motion because of the balance between inertia and gravity. A pendulum operates under Newton's laws of motion and gravity. This, however, is only a simple pendulum. A pendulum is made up of a mass called a bob that is attached to a fixed point. There are 3 key points in a pendulum's swinging motion. The top part that was just reached was the maximum displacement, the furthest distance away from the center of the pendulum. As it swings to their side, it reaches yet another maximum displacement. They are the same thing, just at different parts of the pendulum. The maximum displacements are all equal in measurement. When the pendulum reaches the center and is at the lowest point of its cycle, it has reached the point called the equilibrium point. This coincides with the sine wave, which will be explained next.
So sine waves are based off of the pendulum. A sine wave is a mechanical wave, which is a wave that propagates or spreads through a deformable elastic medium. There are many different types of waves. However, we'll only stick to the mechanical waves because we'll only focus on this one anyway. In a pendulum, the furthest position from the center, or the maximum position, is shown like this, right? When it's swinging back and forth, just like the pendulum you just saw, maximum distance from the center. In a sine wave, it is shown by this. This right here is called the crest. The crest is the highest point from the equilibrium position, which is right here, or right here. The other furthest distance from the equilibrium position is the trough, which is the lowest point from the equilibrium position. And as you can probably tell, the equilibrium position is about here, and these two are equal distances. Now, a wavelength is the distance between 2 adjacent similar points of a wave. So from this shadow, if I can get the shadow, let's see, it would be these 2 points, this point here and this point here. This distance from here to here is a wavelength. Material objects can never occupy the same space at the same time. For example, if I were to stand here, nothing else can be where I am, and we end up colliding. When waves collide or come together, they don't end up bouncing back on each other. This is because waves aren't actually matter. In fact, they're only the displacement of matter. See here, when I tap the top of the water, you see one source of the wave. One source of waves, anyway. Now, when I use 2, you can see 2 different sources of waves coexisting at the same time. This is the same for when I use 3. You can see 3 different sources of waves, but you can see all of them very clearly in the shadow. Same with this one. This is called superposition, which is the overlapping of different waves.
What you just saw was drops of water in a still setting. Now it's disturbing a regular flow. You can see that there are already ripples due to the flow of the water normally. What happens when something stops and interferes with the regular flow? The water is a medium, a material through which a disturbance travels. Waves of almost every type need something to travel. For the waves on a beach, it's water. For sound, it's air.
So here's a sound source. Sound waves come from it, which is, in the example, they're usually sine waves, so it looks like that, but I'm just going to write it like that. And then the ear, it's not a very good ear, receives it. So your ear works as a canal to funnel in sound, and then it goes through your outer ear, and goes into this is the eardrum, which is just in a flap of skin. So it gets the sound wave and it vibrates. And it vibrates by pushing and pulling, and then that makes the noise in your head. And the eardrum is connected to 3 bones called the ossicles. And then that is connected to the cochlea, and this isn't biology, but it connects the nerves, and then the nerves go right to the brain. So for an example of a car horn is about 400 to 420 hertz, which is, if you're playing it on an instrument, it's a B4 or a G flat or G sharp 4. Yeah. So here's an example of the eardrum. It's a thin strip, stretchy.
Right. If you tap the side right here of if you tap one side of the membrane, you can see it rippling on the other side.
That's just like the eardrum, how it collects a sound wave. The tap is like the example of a sound wave. So the sound waves hit the eardrums and it goes through the eardrum and converted into a sound.
Alright, so in the video you just saw with Karun drawing the ear, it shows that thin membranes make it easier to permit vibrations and waves, which are basically the same thing. However, every type of medium will transmit vibrations. The thinner and stretchier the membrane is, the more variety of sound waves you can get. For example, you just saw a latex glove being stretched in water. The latex glove represents the membrane in the ear, which is the eardrum. The water represents the air, which is the type of medium that we just used. And the ripples represents the sound waves. In this example, you're a sponge, an everyday sponge. This basically just shows that everything and anything can vibrate and transmit sounds. However, it's just not as effective as a thin membrane would be, and you're going to see it in this example.
So just like we tapped the eardrum, I'll tap this.
There are still vibrations, it's just not as good as the other one.
Okay, so this is a person in the middle of this place. And this is a car starting right here. This is a terrible car, it's just going to be a box. Okay. And then the car is driving. Oh, I'm going to need that. The car is driving with a horn. So the horn noise, you hear it since it's farther away. The frequency is lower, so the sound waves are wider. They're not as close together because the frequency is less. So the noise you hear is deeper. So then as it keeps going, if the car's right in the middle of you, since it's so close, the frequency is really, really quick, like close together, so the noise you hear is higher. And then once it keeps going, it gets more distance away from you. It goes back to the same frequency that you heard before. So where's the blue? It goes back to the low frequency and a deeper sound.
Okay, so the Doppler effect is a frequency shift that is the result of relative motion between the source of waves and an observer. So basically what you just saw here. From this point of view, the waves are huge, you hear a really low noise, and as it gets closer, it gets louder and louder and louder, and the sound waves get smaller and smaller and smaller, and then same thing as you go away. The sound waves get bigger and bigger and bigger, and then the sound you hear gets lower.